You're listening to DTF Correction Varts for March 21st, 2026. I'm your recursively forked host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where everyone's a skeptic until someone posts a good rewrite. Today feels like a session like that road. There's a pattern worth noticing. Every time a powerful coding assistant gets locked behind a paywall or a terms of service agreement that reserves the right to change everything tomorrow, someone in the open source community looks at it and thinks, we can build that. And then they do. OpenCode is the latest entry in that tradition. An open source AI coding agent that puts the capability where anyone can reach it, modify it, and run it without asking permission. That's not a small thing. Here's what matters about this moment. AI coding agents have moved from novelty to infrastructure. Developers aren't just using them to autocomplete a function. They're using them to navigate code bases, refactor architecture, write tests, debug across layers they didn't write. This is a fundamentally different relationship with your tools. And when your tools are proprietary, that relationship has a third party in it. The company, the platform, the off switch they hold. OpenCode removes that third party. You get the agent, you get the source. You can see exactly what it's doing, modify how it reasons about your code, swap in whatever model fits your needs or your budget or your air-gapped deployment environment. That last one matters more than people talk about. There are entire industries where you can't send your code to a cloud. API, open source agents, are the only path in. The technical architecture of these agents is genuinely interesting. A coding agent isn't just a model sitting in a loop. It's a system that maintains context across a repository, decides when to read files versus when to write them, manages tool calls, handles errors, recovers from wrong turns. Getting that right is hard. Getting it right in the open, where anyone can audit the decisions and contribute improvements, is how you end up with something that compounds. Each improvement available to everyone permanently. The tools exist. The knowledge is available. What OpenCode represents is the ongoing act of not letting that knowledge get enclosed. Someone built the scaffolding and then handed it over. That's bootstrapism in its most literal form. Putting the ladder somewhere others can actually reach it. The question for any coding agent is always the same. Does it make the developer more capable, or does it make the developer more dependent on the platform? Open source answers that question before you even have to ask it. Well, there's a particular kind of scientific momentum that builds quietly until it isn't quiet anymore. Mamba is doing that right now. For context, the transformer architecture has dominated deep learning for nearly a decade. Attention mechanisms, the engine inside every major language model you've heard of, are extraordinary. But they're expensive. Quadratic complexity and sequence length. The longer your context, the more compute you burn, at an accelerating rate. That's a ceiling with consequences. Mamba is the challenge to that ceiling. State space models. Process sequences differently. Instead of attending to every token in relation to every other token, they maintain a compressed hidden state that evolves as you move through the sequence. Linear scaling. Same information, fundamentally different pathway to get there. Albert Gu and Treedau's original Mamba paper landed in late 2023 and immediately earned serious attention. Not hype cycle attention, but the kind where researchers start reaching for their own GPUs. Mamba 2 followed, tightening the mathematical foundations, connecting state-space duality more cleanly, to attention in a way that made the whole framework feel more principled. And now, Mamba 3. Which means the iteration cycle is healthy. This is what productive research looks like. A group of people taking a genuinely good idea seriously enough to keep refining it. What's worth sitting with here is the architectural question underneath all of this. Transformers weren't inevitable. They became dominant because they worked at scale when people scaled them. But works at current scale and optimal for the next decade of compute aren't the same claim. SSMs are the credible argument that we left efficiency gains on the table. That the quadratic cost of attention was a tax we kept paying because we didn't yet know how not to. The open research community is where this gets solved. Gu and Dao published. Other groups picked it up, stress-tested it, found the failure modes, proposed fixes. That's the loop. Mamba 3 exists because Mamba 1 was public and people could actually work with it. Run this forward. If SSMs mature in production-grade alternatives to transformers, the compute efficiency gains compound everywhere. Smaller models with equivalent capability, longer contexts at the same cost, deployment on hardware that never could have run a transformer at this scale. That's not a minor footnote. That's the whole game-changing shape. 2. FFmpeg is quietly running inside almost every piece of software that touches video or audio. YouTube uses it. VLC uses it. Discord uses it. Thousands of apps you've used today have FFmpeg somewhere in the stack. Doing the unglamorous work of transcoding, muxing, filtering, and converting media from one form into another. It has been doing this reliably and without complaint since 2000. And yet, ask most developers how to actually use it, and you get a shrug and a Stack Overflow link. That's the gap FFmpeg 101 is trying to close, not by simplifying the tool, but by teaching it. There's a meaningful difference. FFmpeg is complex because media is complex. Codecs, containers, bit rates, frame rates, pixel formats, stream mapping. These aren't artificial complications. They're the actual texture of the problem. A tutorial that papers over this complexity does you a disservice. One that walks you through it builds genuine capability. Here's what makes FFmpeg worth learning in 2024 specifically. The landscape of media processing has never been more important. You've got AI-generated video, podcast pipelines, local transcription workflows, surveillance systems, streaming infrastructure. All of it touching media, all of it benefiting from someone who actually understands what's happening at the codec layer. FFmpeg is the lingua franca. If you can speak it, you can work anywhere in that stack. The tool itself is a triumph of open source, so the FFmpeg project takes contributions from hundreds of developers, supports an almost incomprehensible range of formats, and ships under LGPE or GPL licenses that let you build on it commercially. No vendor lock-in, no pricing tier that gates off to a middle 265 support. No terms of service that change when the company gets acquired. You download it, you run it, it works. That's the bootstrap in action. Someone did the hard work and then put it where anyone could reach it. The tools exist. The knowledge is available, especially now. An FFmpeg 101 guide in 2024 means one fewer developer who stares at a cryptic command and guesses, and one more who understands what they're actually asking the machine to do. That compounds. People who understand their tools build better things, debug faster, teach others. This is what open source wins look like. Not dramatic announcements, but capability spreading quietly outward, one tutorial at a time. There's a Japanese term, melibashi, for when you hover your chopsticks over dishes, unable to decide what to eat. Wandering chopsticks. And the fact that this behavior has a name, a dedicated word, cataloged alongside a dozen other transgressions, tells you something about how seriously a culture can take the poetry of an everyday object. The glossary of chopstick faux pas is genuinely one of the more delightful corners of cultural documentation you'll find. These aren't arbitrary rules handed down by etiquette scolds. Most of them have roots that go back centuries, and once you know the roots, the rules stop feeling fussy and start feeling like a window into something real. Take a shiwatashi, passing food directly from your chopsticks to someone else's. It's the one that surprises Westerners most, because it looks like sharing, which is supposed to be good. But in Japanese funeral tradition, the bones of the cremated are passed between family members exactly this way. Chopstick to chopstick, as they're placed in the urn. So when you do it at dinner, you're not being generous. You're accidentally staging a funeral. The table reads it as wrong before anyone consciously processes why. Or tatabashi, standing your chopsticks upright in a bowl of rice. Same resonance, offerings to the dead. You've turned your meal into a shrine, which is not the energy you want at a celebratory dinner. What I find genuinely fascinating here is the compression. These rules encode an enormous amount of cultural memory into a single gesture. The prohibition on teibashi isn't just, don't do that. It's rude. That gesture means something. It means death and offering and grief. And we've agreed as a culture to keep that meaning alive by never accidentally invoking it over soup. That's not superstition. That's a society maintaining its own symbolic infrastructure. Meaning requires maintenance. The rules are the maintenance. There's also something wonderful about the fact that someone compiled this into a glossary named Every Offense and put it somewhere findable. Knowledge that used to live only in households, transmitted by grandmothers and watchful relatives, now exists as a document anyone can read. The glossary is itself a kind of preservation technology. Mundane objects, handled with intention, carry whole worlds inside them. Chopsticks have been doing this work for a very long time. There's a piece of hardware folklore so good it became a design philosophy. A molly guard is a physical cover, a flip-up shield, a recessed button, a hinged plastic cap, placed over something you really do not want to press by accident. The name traces back to a small child named Molly, who, with the innocent curiosity of a child, found the large satisfying red button in a machine room and pressed it. The button was an emergency power cutoff. The machine room went dark. The engineers, once they had restored order and perhaps taken a breath, installed a cover. They called it a Molly guard. What I love about this is the response. No scolding, no blaming the child, no locking the room. Just a quiet acknowledgement that human beings, small ones, tired ones, distracted ones, will do what human beings do, and the system should be designed around that fact, not against it. The concept migrated from hardware into software. There is a Debian package called Molly Guard, still maintained, that intercepts shutdown and reboot commands when you are connected via SSH. It asks you to type the host name of the machine before it lets you proceed. Because the number of production systems accidentally rebooted by an engineer who forgot which terminal window was which is, let us say it is a large number, the Molly Guard does not assume malice. It assumes humanity. This is what good system design looks like. It encodes empathy. It asks, what will a real person under real conditions actually do? And how do we build something that protects them from the worst version of that moment? Run this forward. The best security is not the lock that stops attackers. It is the design that prevents the catastrophic accident before it starts. The best interface is not the one that assumes a careful expert. It is the one that catches the exhausted one at 2 a.m. who is one keystroke from a very bad day. Hacker culture produced this idea and then open-sourced it. The package is free. The philosophy is free. The name is a small memorial to a child who pressed a button and inadvertently made every machine room slightly more humane. That is the kind of thing that matters. A team rewrote their Rust WebAssembly parser in TypeScript, and it got faster. Not a little faster. Faster in a way that made them question their assumptions, which is the best possible outcome from a rewrite. Let's pull this thread. The conventional wisdom goes like this. Rust is fast, WebAssembly is fast. Therefore, Rust compiled to WebAssembly is the move when you need a high-performance parser running in the browser. The logic is seductive. Rust gives you memory safety without garbage collection. WASM gives you near-native execution. Stack those advantages and you're set. Except the boundary matters. Every time JavaScript calls into a WebAssembly module, there's overhead. Data has to cross the membrane. Strings get copied. Types get marshaled. The runtime has a context switch. For a parser, that's doing thousands of small operations. That boundary crossing adds up fast. You're not bottlenecked on compute anymore. You're bottlenecked on the handshake. TypeScript, running directly in V8, doesn't have that problem. V8's Jet compiler has been in continuous refinement for over 15 years. It knows how to optimize hot loops. It knows how to inline. It knows the shape of your objects. When the code is right there in the engine's native environment, the Jet can work its full range of tricks. This is the kind of thing that matters. Not because Rust is bad or WASM is oversold, but because the lesson generalizes. The right tool is almost never the abstractly fastest tool. It's the tool that's fastest given the actual execution context, the actual call patterns, the actual data flow. WASM is genuinely powerful for CPU-bound work that operates on large contiguous data, for a parser deeply entangled with JavaScript's runtime. You're fighting the architecture. There's something worth sitting with here. The team that rewrote this probably spent real time building the Rust version. They had reasons. Those reasons weren't crazy. And then they measured, and reality disagreed. And they followed the measurement. That's the discipline. Instrument first. Understand where time actually goes. Then optimize at the real bottleneck. Not the imagined what. The tools exist to measure. The knowledge is available. The only thing that leads people astray is skipping the part where you look. The motto on the Ghostling repository is in Latin. Ex minimo infinita nascentur. From the minimum, infinite things are born. That's not just branding. It's a technical thesis. Ghostling is a new project from the Ghosty team, and the premise is deceptively simple. It's a fully functional terminal emulator in a single C file, uses raylib for rendering, builds on libghosty, which is the embeddable core they extracted from the Ghosty terminal itself. The whole thing is a demo. A proof of concept designed to show developers exactly what you can build on top of their library. Here's what makes this interesting. Ghosty shipped to enormous enthusiasm when it launched. Fast, native, genuinely good terminal emulator. But the bigger play was always libghosty. That's the core. VT sequence parsing, terminal state management, cursor position, text reflow, scrollback, SIMD optimized parsing, full Unicode support, KDE keyboard protocol, mouse tracking, zero dependencies, not even libc. That core is now available to any application that wants to embed real terminal emulation, not reinvent it. Ghostling is what you get when you drop that core into a minimal shell. One file, full 24-bit color, bold and italic, resize with text reflow, keyboard input with all the modifier support you'd expect. And it works. The HN comments are already building. One developer shipped a full macOS terminal in 2 weeks. Swift AppKit vertical tabs and notifications that fire when an AI agent finishes a task. They're using it as their daily driver over iTerm. Another project called Trolley is using libghosty to package TUI apps as desktop applications. Same idea as Electron, but for the terminal. Someone else embedded it in an agent management tool. 2 weeks since the post, and the ecosystem is already seeding. Run this forward. What you're watching is the commoditization of terminal emulation, not the glamorous part of infrastructure, but exactly the right kind of open move when the hard problem. Accurate, fast, well-tested terminal state becomes a library anyone can pick up. The cost to build novel terminal experiences collapses. Custom interfaces, embedded terminals in IDEs, agent dashboards that actually understand what's happening in the shell, packaging TUIs for people who've never opened a terminal. That design space just got a lot cheaper to explore. The tools exist. The knowledge is available. Ghostling is one file that proves it. Fujifilm has a piece of software called X RAW STUDIO. If you shoot with their cameras, you probably know it. It processes RAW files using the camera's own hardware. You plug in your X-T5 or your X100VI via USB, and the software offloads the computation to the camera's image processor. The idea being that the camera itself knows how to render its own files better than any generic converter running on a CPU. It's a clever architecture. It's also deeply proprietary, platform-locked, and requires you to have the physical camera connected to use it. Which means if your camera is in your bag, on a trip, lent to someone, you're stuck. The tool and the hardware are fused by design. Someone decided that was unnecessary. They built a web app clone. Run this forward for a second. Everything Fujifilm software does. The film simulations, the tone curves, the grain rendering, the color science that photographers pay a premium to access. Someone mapped that, understood it well enough to replicate the interface in the workflow, and shipped it as a web application. No USB cable, no platform requirement. Open a browser, load your RAW files, process them. This is what happens when software is studied rather than trusted. Fujifilm didn't publish a spec. They didn't open source their film simulation algorithms. But the outputs are observable, the parameters are finite, and people who care enough will reverse engineer what they need. The knowledge exists, the tools exist. The only thing standing between a locked system and an open one is someone with enough curiosity and time to close the gap. The interesting thing about Fujifilm specifically is that their film simulations, Classic Chrome, Eterna, Acros, are genuinely beloved. They've built a community around aesthetic choices. Baked in the hardware, that's real value. And now that value is more accessible, not less. More people can work with Fujifilm files. More people can experiment with their look without owning their ecosystem. That's not a threat to Fujifilm. That's advertising. The web app clone doesn't replace the camera. It removes an artificial bottleneck between the camera's creative output and the people who want to work with it. The tools exist. The knowledge is available. Someone put them where others can reach them. That's the whole game, really. Tausa! There's a book that keeps showing up in programmers' lives at exactly the right moment. Linux Applications Programming by Example. The second edition just surfaced on Hacker News, and the reaction tells you something important about where we are right now. Here's what this book is. At its core, a manual for talking to the kernel. The fundamental AP is read, write, open, close, fork, exec. The syscalls that sit beneath everything you've ever run on a Linux machine. every web server, every container, every machine learning framework. At the bottom of the stack, it's these calls. Always has been. The reason this matters in 2025 is that we have a generation of developers who've built extraordinary things on top of extraordinarily high abstraction layers. Frameworks on frameworks on frameworks, which is fine. Abstraction is how you get things done at scale, but there's a fragility that comes with not knowing what's underneath. When something breaks at the wrong layer, you need to be able to read the terrain. This book puts the terrain on the table. What's remarkable about Linux's API surface is how stable it is. Linus famously will not break user space. The system calls documented in a book from 15 years ago still work. That's not an accident. It's a design philosophy. The kernel is a promise. Write to these interfaces, and we will not pull them out from under you. That kind of stability is genuinely rare. It's the kind of thing you can build a civilization on. And arguably, we have. There's something worth sitting with here. These APIs are documented. They're open. Anyone can read the source. Anyone can write a book explaining how they work and publish it. The knowledge is available. The tools exist. The interface is stable and public and maintained by thousands of contributors who answer to no single company with an incentive to lock you in. Run this forward. Every programmer who understands these fundamentals is more capable, more autonomous, harder to lock into proprietary ecosystems. Every system built on Linux's open API surface is a system that can be inspected, understood, modified, and replaced. That's not just technical education. That's infrastructure for agency. Pick up the book if you're missing this layer, or find it in a library, or find the older edition for free somewhere on the internet, because knowledge like this has a way of escaping into the open where it belongs. Picture this. No GS Thurn, no GPS, no excavators worth mentioning, no diesel engines, and a man named William Mulholland decides to move a river. 233 miles of it, over mountains, through DEH Zert, across terrain that would make a modern civil engineer reach for the bourbon. The Los Angeles Aqueduct is one of those engineering achievements that sounds impossible until you realize it actually works by gravity alone. Mulholland's team surveyed the entire route by mule. They blasted through the Tehachapi Mountains with hand-drilled dynamite. They built a temporary railroad just to haul supplies. Then built the aqueduct. Then dismantled the railroad. The whole project took 5 years and employed thousands of workers living in tent cities scattered across the Mojave. And when it was done, Mulholland opened the gates, watched 26,000 acre-feet of Owens Valley water pour into the San Fernando Valley, and said, "And this is real. This is the actual quote." There it is. Take it. The engineering is genuinely staggering. The aqueduct drops about 2 feet per mile through most of its length, just enough gradient to keep the water moving without pumps. Where it crosses the Antelope Valley, it runs through inverted siphons. Water drops into a buried pipe, pressure builds, it climbs back up the other side. The longest of those siphons runs 5 miles. They built this with 1900s technology and it's still operational. But here's where the story gets complicated, because it always does. The water didn't just appear. The Owens Valley had farms, ranches, a functioning agricultural economy. The water rights were acquired through a process that the people who lost them described, with considerable justification, as theft. The valley was drained. The farms failed. Owens Lake, a real lake, you can look at old photographs, became a dry alkali flat, now the largest source of dust pollution in the United States. LA grew. The Owens Valley didn't. Infrastructure shapes who gets to exist and where. The Aqueduct made 10 million people possible in a DEH-ZERT. It also made a decision about whose water that was and who got to answer that question. Those decisions compound across generations. That's why the history of water in the American West reads less like engineering and more like a lesson in who controls the infrastructure. Mulholland built something extraordinary. The question of whether it was built right is still being litigated. Sometimes literally. This has been your daily tech feed for Hacker News for March 21st, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voice by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go put something where others can reach it. We'll see you back here tomorrow.